Greetings and welcome to the Chemistry 222 video for problem set number 5, and I'm glad to have you here. We're going to look at chapter 11 in this section. This is the chapter on solutions, so it's kind of interesting stuff, and solutions are super helpful to chemists. Anyway, like the other problem sets before, I encourage you to use a periodic table, have it next to you. mhchem.org/pertab is the one I'd like you to use. Before you turn in your problem set to me at the beginning of lab, make sure that you self-correct your problem set. That means put symbols next to both the problems which you got correct and next to the problems which you got incorrect. So next to the problems you got correct, put some kind of self-correct symbol, like for example, the check mark is fine, a star, smiley face, whatever you'd like. And next to the problems which you missed, which by the way, it's okay to miss problems on this, put some kind of marks next to it so that you can at least know the correct answer. So put down the right answer, maybe put some notes as to how you would do it right the next time. You turn in a problem set without any self-correct marks, even if every question is right, you will not get full credit. On the other hand, you turn in a problem set to me which is self-corrected every problem. Even if you missed every problem, you will still get full credit. So it's pretty important. If you have questions on the material, please reach out to me. You can also talk to the AVID/LSC Center located above the library on the main MHCC campus. The website is mhcc.edu/avid. They offer free chemistry tutoring to you as an MHCC student. I encourage you to check them out. So without further ado, let's get into the problem set and see what this material has to offer. We've got a table, all right, and this table is going to ask us how to convert from one of our new concentration units to the other. So as an example, in the first one, the first row right there, you can see it says KNO3, and it says that all solutions are aqueous. Aqueous means water. So in this problem, KNO3 is the solute and water is the solvent. So in this first equation, we're starting with a 10% KNO3 aqueous solution, and it says what's the molality and what's the mole fraction. Simple, no problem. Anyway, nothing you can't handle. The second one, CH3CO2H, that's acetic acid, and we're starting in this problem with a molality. So we've got acetic acid in water, and we want to take that molality and turn it into weight percent and mole fraction. And the third row, the third part of this problem, this compound here is called ethylene glycol. It's a diol, a double alcohol. In this problem, which is also dissolved in water, by the way, we're starting with a mole fraction, and we want to turn mole fraction into weight percent and molality. So these are all real useful skills in this chapter because we're going to use all three of these types of values, and it's nice to know how to interconvert one to the other. That's a big part of this section. Here are the answers. The parts in bold are the answers. And on the next several slides, I'm going to show you in greater detail how we got these numbers. But for right now, what I would do is just check them off. If you got the answers right, you can skip through my lecture on it. On the other hand, if you didn't get the answers that I got or weren't very close to them anyway, you might want to pay attention and see how these kind of processes work. To solve these problems, we need the definitions of molality, weight percent, and mole fraction. So molality, which gets the symbol little m, it's moles of solute per kilogram of solvent. Weight percent of A in a mixture would be essentially the mass grams of A divided by grams of everything else. So if there's A, B, and C, you'd add them all together. If there's only A and B, then it would be grams of A divided by grams of A plus grams of B. You multiply this one by 100%. It is a percentage, no problem. And then mole fraction, which gets the symbol chi. It looks like an X, but it's not really, but you can write it as X, that's fine. Anyway, mole fraction of A is moles of A divided by total moles. So most of these will have just two components, solute and solvent. So it would be like moles of solute over moles of solute plus moles of solvent. Mole fractions are always numbers between 0 and 1. And weight percents, likewise, are numbers between 0 and 100. I guess technically neither one of them would be 0 if you're really looking at it. I guess it would show it wasn't there. Anyway, I digress. Let's see how this stuff works out now. In the first question with KNO3, we're going to assume that we're going to start, by the way, with its 10.0 weight percent KNO3. And if you have a weight percent, I would start by assuming you have 100 grams total. If you have 100 grams total, then you have 10 grams of solute and 90 grams of solvent. So notice how that 10.0, it refers to the grams of KNO3, the solute. And if we had 100 grams total, then 100 minus 10, we would have 90 grams of water, 90.0 grams of water, the solvent. Now, in all of these problems in question 9, it's a really good idea to have grams and moles of solute and solvent. And in this problem right now, we have grams of solute, the KNO3, and grams of solvent, the water. But we should turn both of those numbers into moles in order to do mole fraction, etc., etc. So the next part, I just turned those grams into moles. Again, you want to have grams and moles of both solute and solvent. So KNO3, if you add that up, the molar mass, 101.1 grams per mole. So 10 grams divided by that, 0.0989 moles KNO3. Water's molar mass, about 18.02 grams per mole. So 90 grams divided by that, 4.99 moles of water. Now, once you have grams and moles of anything, you're ready to rock and roll. Because, for example, molality will be moles of solute, the 0.0989 moles KNO3, divided by kilograms of solvent. So 90 grams divided by 1,000, that's going to give you the kilograms. And mole fraction will be moles KNO3 divided by moles KNO3 plus moles water. So if you look at the math, here's the molality first, all right? Moles KNO3 divided by kilograms of water, plug and chug those numbers, 1.10 molal. Mole fraction KNO3, moles KNO3 divided by moles KNO3 plus moles of water, 0.0194. So pat yourself on the back. This is freaking awesome. You have the first row of this problem done, and that's no small feat. You can see in the top row, I filled in the KNO3 values since we did that on the last one. This next one we're going to look at in row number 2, it involves the compound CH3CO2H. That compound is acetic acid, aka ethanoic acid by its formal name. That's the active ingredient in vinegar, but that's not really important here. We're starting with 0.0183 molal of an acetic acid solution. And just like in the last problem, we assumed that at 10% weight percent, we had 100 grams, and we were able to find grams of solute and grams of solvent. For molality, what we want to do is we want to assume that we have exactly 1 kilogram of solvent. And again, our solvent here is water, so that means we have 1,000 grams of water, 1,000 grams per kilogram. That also means then, if we have exactly 1 kilogram, that we have 0.0183 moles of solute, the acetic acid. So like I said earlier, you want to have grams and moles of both solvent and solute. We have moles of solute, so we need to convert that into grams of solute using the molar mass. We have grams of solvent, but we want to turn that into moles of water using the molar mass of water. So this next part is just me doing that. I'm taking the 1,000 grams, turning it into moles, 55.5 moles of water. 0.0183 moles times about 60 grams per mole, that's the molar mass of acetic acid, 1.10 grams acetic acid. So now we've got grams of solute and solvent. We have moles of both solute and solvent. So now we can start figuring out weight percent and mole fraction. So weight percent here would be the grams of the acetic acid, the solute, and I would divide it by grams of acetic acid again, plus grams of solvent. So 1.10 plus 1,000 would be on the bottom, and the top would be 1.10. We'll multiply that all by 100%, 0.110%. Not a lot of acetic acid in this particular situation. That's the weight percent of acetic acid. Now the mole fraction will just be moles of acetic acid divided by moles of acetic acid plus moles of water. And again, these numbers will be somewhere between 0 and 1 usually. This is 3.30 times 10 to the minus 4. Pretty small, not a lot of acetic acid. But again, if you got those numbers, well done. And if you don't, I want you to go through this example. Make sure you can do all the math. Make sure in the denominator, when you're adding things together, you put a parentheses around both numbers. That's really important. This is all stuff you can do. So again, there I filled in those two numbers, and we're going to look now at the last example, which is with the HOCH2CH2OH. This compound is called ethylene glycol. It's a diol, and we're starting on this one with mole fraction, 0.0599. If you start with mole fraction, then what I would do is assume that you have 1 mole total. If you have 1 mole total, then that means 0.0599 is going to be the moles of solute, the ethylene glycol. And 1 minus 0.0599, that's going to be the moles of solvent, which is water. So now this is how you get moles of solute and moles of solvent. The number for mole fraction literally is the moles of solute, and 1 minus that number, moles of solvent. Now from moles of both solute and solvent, you can go to grams of solute and solvent. Ethylene glycol is about 62.07 grams per mole, so you get 3.72 grams of ethylene glycol. Moles of water times 18.02 gives you grams of water. And notice there that I turned it into kilograms because I'm already thinking about molality. Molality, the first of our units, moles of solute divided by kilograms of water. And in this problem, we had 0.0599 moles ethylene glycol divided by 0.01694 kilograms, 3.54 molal. And then finally, the last one, weight percent, grams of ethylene glycol on top divided by grams of ethylene glycol plus grams of water. Remember to put a parenthesis around that one, times 100%. This is 18.0% ethylene glycol. Whew. So anyway, this is how you do those problems. So notice that all of these had an assumption to begin with, and that's the part that sometimes people don't see. Once you know what that assumption is, the next goal is just to get grams and moles of both solute and solvent. And from there, you can find all these kind of units. These problems will fall for you. The king of all the units of concentration in chemistry is definitely molarity. And molarity is different from mole fraction, weight percent, and molality. Molarity has moles of solute per liter of solution. So not only do you have volumes instead of moles and grams and kilograms, but you also have solution. The other ones were just solute and solvent. So this is a good problem to see how this process works. And there's more than one way to do these kind of problems, by the way. If you're going to go from molarity to the other three, mole fraction, weight percent, or molality, or if you're going from those three back to molarity, you will need the density of the solution. So this 1.84 number we haven't had to use yet because we haven't had to go from molarity to one of the other ones or from one of the other ones to molarity. But on this one we will. So in this problem, we have a concentrated aqueous sulfuric acid solution. Sulfuric acid, H2SO4, is our solute, and water is the solvent, aqueous once again. It's 95.0% H2SO4. So just like we saw in the last problem, if we assume 100 grams total, that means we'd have 95.0 grams H2SO4 and only 5.0 grams of water. We can use this information to calculate both the molarity and the molality. Now, assuming again you start with 100 grams, that means you have 95 grams of solute, H2SO4, and 5.0 grams of water, the solvent. Now, molality is moles of solute, H2SO4, divided by kilograms of solvent water. Let's take the 95 grams, turn that into moles of H2SO4. H2SO4 about 98.08 grams per mole, so that's 0.96 0.969 moles sulfuric acid. If you take that moles and you divide by the 5 grams of water in kilograms, so 0.0050, that's 5 divided by 1,000. Anyway, you end up with a molality, 190 molal. It's 2 sig figs because we only had 2 sig figs up there. So the 2 sig figs goes all the way down, 190 molal. Now, for molarity, we need moles of solute over liters of solution. And we already have the moles of solute number, that number right there. We need liters of solution. The 1.84, that's the density of the solution. It's 1.84 grams of solution over a milliliter of solution. So the way that I would do this problem is I would say, hey, we have 100 grams of solution. That's with solute and solvent. So if you take that number, divide it by the density, a centimeter cubed is the same as a milliliter, and there's 1,000 milliliters per liter. This comes out to be 0.0543 liters of solution. So notice that solute plus solvent equals solution. 100 grams literally is the grams of the solution. And you can turn that into liters of solution, and then molarity, 0.969 moles, the same number from before of sulfuric acid, divided by 0.0543 liters, 17.8 molar. So this is how you go from, in this case, mass percent, weight percent, into molality, which we've already seen, but also into molarity. And there's similar kind of things if you start with mole fraction and go to molarity, or molality and go to molarity. One little trick I can share with you, almost always molarity will be a number less than molality. So you can see that 17.8 molar is quite a bit less than the molality, 190 m, and almost always that's the case. So if you calculate a molality which is bigger than your molarity, probably something is wrong, FYI. Silver ion has an average concentration of 28 parts per billion in the U.S. water supplies. And it says, what's the molality of the silver ion? And B, if you wanted 1.0 times 10 to the second, which is 100 grams of silver, and you could recover it chemically from water supplies, what volume of water in liters would you have to treat? And let's assume the density is 1 gram per centimeter cube. All right, parts per billion, as well as parts per million, parts per trillion, parts per thousand in this context, is another kind of concentration unit. In a parts per billion, it means in this case you would have 28 grams of silver in a billion, or 10 to the 9th grams of water. If it was a part per million, it would be 28 grams of silver in a million, 10 to the 6 grams of water. And yes, you can have a parts per thousand, which would be 28 grams of silver and 1,000 grams of water. That parts per thousand is different than the parts per thousand we use in lab. In lab, we're measuring the precision, how close the experiments are to each other. This is actually more like a molarity or a molality. It's a true concentration. So knowing that this is 28 parts per billion, which is like 28 grams of silver in a billion grams of water, you can turn those units into molality, into moles of silver per kilogram of water. Here's again the definition. We're using here parts per billion. So that's 1 gram of solute, silver in this case, divided by a billion, or 10 to the 9th grams of solvent, which is water in this case. So again, 28 grams per 1 billion grams of water. You can turn the grams of silver into moles in the first step. 1,000 grams per kilogram. So you can see here that the grams are canceled, the grams of silver are canceled, and you have moles of solute, silver, per kilogram of water, 2.6 times 10 to the minus 7th molal. Now in the last problem we had a molality of 190 molal. This number is obviously a lot smaller. That means there's not a lot of silver in the U.S. water supplies, okay? And that'll be kind of a segue to the second part of this question. But if you need to convert it, no problem. A billion is 28 parts per billion, would be 28 grams of silver per billion grams of water. You can go from there. Good to go. The second part says that we want to extract 1.0 times 10 to the second grams of silver. And how much water would we have to treat? Okay, well, 100 grams of water, and what we can do is use that parts per billion. It's 28 grams of silver per 1 billion grams of water. And if you assume the density is 1.0 grams per centimeter cubed for water, that grams of water will equal milliliters of water. So there's 1,000 grams in 1,000 milliliters, if you will, and there's 1,000 milliliters per liter. This comes out to be 3.6 times 10 to the 6 liters of water. And I want you to think about that number. That's 3.6 million liter containers of water. And you're probably familiar with a 2-liter container, which is what they put soda pop and stuff like that in stores. That would be 1.8 million of those bottles you'd have to go through to get 100 grams of silver out. And that also assumes that you have 100% efficiency, like you literally get all of the grams of silver out, which probably isn't going to happen. So once in a while, for my job at Mount Hood, somebody will come by my office and stuff and say, "Hey, Russell, you want to get rich?" And I'm like, "Heck yeah, I want to get rich. Oh yeah." And they say, "We're going to get all this money out of seawater and river water and stuff like that." And right away I'm like, "Oh, come on, that's it." And I shut my door on them basically, because you can't do it, man. You'd have to go through just so much water to get 100 grams of silver out. Maybe. That's assume you have 100% yield, right? And that's not going to happen. This is such a small amount of silver for a lot of water. It's going to take forever to do it. So be wary if they're going to try and make you money this way. Hydrogen gas has a Henry's law constant, 1.07 times 10 to the minus 6 molar per millimeter of mercury at 25 degrees Celsius when dissolved in water. Now, if the total pressure of the gas, which is hydrogen plus water vapor, over the water is 1 atmosphere, what is the concentration of H2 in the water in grams per milliliter? The vapor pressure of water, 23.8 millimeters of mercury. This question goes back to a question we saw in problem set number 4. If you're collecting a gas over water, which is actually very common, then the total pressure, which in this case is 1 atmosphere, equals the pressure of the H2, which is what we want, plus the pressure of the water. And the pressure of the water in this problem, 23.8 millimeters of mercury. So the first thing, in order to use Henry's law and go into all those different conversions, we have to get the pressure of the hydrogen by itself. So we're going to take 1 atmosphere, which is 760 millimeters of mercury, subtract 23.8 millimeters of mercury from it, 736.2. That is the partial pressure of hydrogen gas in this example. The other part of the pressure is the water, but we don't want that when it comes to Henry's law. Henry's law is always specific for a particular type of gas. Now, once you have this number, you can see this weird Henry's law constant. It's molar per millimeter of mercury. If we multiply 736.2 by that 1.07 times 10 to the minus 6, the millimeters of mercury are going to cancel out, and you're going to be left with molarity. And that is a type of concentration. So the 7.88 times 10 to the minus 4, that says you're going to have that many moles of H2 dissolved per liter. And that's kind of a cool thing unto itself. But most of the time, people that aren't in science, heaven forbid, anyway, people that aren't in science, they would rather hear about how many grams dissolved per milliliter or pounds per yard or something like that. Anyway, there's other kinds of units. So let's say that no one here wants to talk about moles per liter, but they want to talk about grams per milliliter. Okay, no problem. So 7.88 times 10 to the minus 4, that's how many moles of H2 there are per liter. So the first thing, you can get rid of the liters by dividing by 1,000. A mole of H2 on the periodic table, 2.016 grams. This comes out to be 1.59 times 10 to the minus 6 grams per milliliter. So every milliliter of this water should have 1.59 times 10 to the minus 6 grams. Not too hard to do. Pretty cool. Remember to subtract the water vapor from the total pressure if you're dealing with a gas over water. But otherwise, I think this stuff is pretty straightforward. Non-volatile urea, which has the symbol NH22CO, is widely used in fertilizers and plastics. It's quite soluble in water. We're dissolving 9 grams of urea in 10 milliliters of water. What is the vapor pressure of the solution at 24 degrees Celsius? We're going to assume that the density is 1 gram per milliliter and the vapor pressure of water 22.4 millimeters of mercury. Okay, this is the first of our colligative property questions, and this question is about vapor pressure. And the vapor pressure of a solvent in a solution is less than the vapor pressure of the pure solvent. 22.4 millimeters of mercury. That's the vapor pressure of pure water. And the number we're going to calculate will be a number less than 22.4 because the solute, which is this urea stuff, is going to block the water molecules from going from the liquid to the gas. So vapor pressure is lowered over in the solution relative to the pure solvent. Now, in order to do this problem, we need the mole fraction of the solvent. This question is a Raoult's law question, and Raoult's law says to take the mole fraction of the solvent times that 22.4. So I took the 9 grams of urea and turned that into moles, and that's that number right there. 10 milliliters of water at the density of 1 is like the same as grams, 18.02 grams per mole, so 0.555 moles of water. So now I've got moles of solvent, I've got moles of the solute, urea. Remember, in these problems, you want mole fraction solvent. So it's 0.555 divided by 0.555 plus 0.150. Mole fraction of solvent, not mole fraction of solute. So if you did this right, the mole fraction of the water, 0.787. You can multiply the mole fraction of the solvent by the 22.4, the vapor pressure of the pure solvent, and this number comes out to be 17.6 millimeters of mercury. So notice here, in the pure solvent, the vapor pressure 22.4, but in the solution, the vapor pressure was lowered. The urea is blocking the liquid water from going into the gas phase. So the vapor pressure is less in the solution, 17.6, than it was in the pure solvent, 22.4. Raoult's law sounds funny and feels weird when you first see it, but honestly, it's pretty chill as long as you remember to use mole fraction solvent. Most of the time we're after mole fractions of solute, molality of solute, etc., etc. This is the one time where mole fraction solvent is really important. And remember, your final answer should be less than the vapor pressure of the pure solvent. What is the boiling point of a solution with 0.755 grams of caffeine? Woohoo, favorite molecule. Sorry, couldn't resist. Anyway, put that many grams of caffeine in 95.6 grams of benzene, and benzene is C6H6. The normal boiling point for benzene, 80.10 degrees Celsius, and the boiling point constant, that's the KBP, 2.53 degrees Celsius per molal. This is another one of the colligative properties. This is boiling point elevation, and solutions will have higher boiling points than the pure solvents. So if benzene normally boils at 80.10, the solution with caffeine will have a higher boiling point. So at the end here, our final answer should be a number larger than 80.10. All right. On this one, on both boiling point elevation and the freezing point questions we'll see, it's all about delta T equals K times M. And because this is boiling point, I'm going to put a delta T BP and a KBP. You could replace that with FP or MP, freezing point, melting point, something like that. When you get to the freezing point, same thing. But anyway, we do need the KBP, which is that 2.53 number. But we also need the molality, the moles of caffeine divided by kilograms of solvent, kilograms of benzene. Caffeine has a molar mass of about 194.2 grams per mole. So 0.755 divided by the molar mass will give you the moles. We're going to divide that by 0.0956 kilograms. That's 95.6 divided by 1,000. The molality here comes out to be 0.0407 molal. That's the molality of the solution. Now we've got molality and we have the boiling point constant, 2.53. We'll multiply those two together to get the change in the boiling points. And that change, that delta T, 1.03 degrees. So if caffeine normally boils, or thanks for playing, if benzene normally boils at 80.10, the benzene caffeine solution will be 0.103 degrees higher. So 80.10 plus 0.103, we have to cut it off at the hundredths mark because that's the doubtful digit, all that kind of stuff. 80.20 degrees Celsius. So the boiling point of the solution is higher than the boiling point of the pure solvent. And this is what they call boiling point elevation. All right. You can use water. You can use benzene like you did here. There's a whole bunch of solvents. Each one of them will have their own KBP value, and you never have to memorize those. I will always give you those values to use. Some ethylene glycol, which we saw earlier, added to the car's cooling system with 5 kilograms of water. All right. If the freezing point of the water ethylene glycol solution is negative 15 degrees Celsius, what mass of ethylene glycol must have been added? Now, the normal freezing point for water is 0 Celsius, and KFP, the freezing point constant for water, 1.86. Now, this is also a delta T equals K times M problem, but this is a freezing point question. So while the last problem had BPs for boiling points, this one's going to be delta T FP for freezing point. Sometimes you see delta T MP for melting point, whatever. I don't know which one you want to use, but it's really freezing because you're going from a liquid to a solid. Anyway, whatever you want to use is totally fine. Now, sometimes your KFPs are going to be listed as negative numbers, and sometimes the delta T values are listed as negative. So you take the normal freezing and you subtract it from it. I want you to know more than anything else, you must have molality be a positive number. So you absolute value that molality if you need to. Molality is based on moles, and moles is based on grams, which is mass. And in chemistry, all mass is positive. There's no negative mass. So you can have negative or positive, delta T's or K's, I could care less. But man, you make sure your molality is a positive number. You can't have negative mass in chemistry. So molality must be a positive number. So in this problem, all right, there's different ways to do it. Your freezing point is 15 degrees lower than 0. So there's a couple ways you can do delta T. I would just say, hey, freezing point 15 degrees less, that's the positive number I need. It lists KFP here as a positive, but again, you can have negative for one of them or negative for both of them, whatever, I don't care. You just make sure that that molality is a positive number. So I don't care if your delta T's and K's are positive or negative, you make sure your molality is a positive number. That's most important, okay? Everything else is secondary. Now, 8.06 is the molality of this ethylene glycol water solution, and that means 8.06 moles of ethylene glycol per kilogram of water. Well, in this problem, we have 5 kilograms, so let's knock out the kilograms of water, and moles of ethylene glycol to grams, we'll use the molar mass, 62.07 grams per mole. This number comes out to be 2,500 grams of ethylene glycol, or 2.5 kilograms. So if you put 2.5 kilograms or 2,500 grams of ethylene glycol in with 5 kilograms of water, the freezing point of your solution will be at -15. And if you live in a really cold place, this is good. You don't want to have a cracked radiator or something like that. So it can be a really cool thing to know. We're putting some BHA, which is some kind of nasty compound, I think. But anyway, I digress. BHA, 0.640 grams in 25 grams of chloroform. So BHA is the solute, chloroform is the solvent. And the boiling point of the solution is 62.22 degrees Celsius. The boiling point of pure chloroform, 61.70. So you can see the boiling point went up in the solution relative to the solvent. We also need a boiling point constant for the solvent, chloroform, which is right there. And all of this stuff is going to give us the molar mass, all right? Remember, molar mass, the grams per mole, that's kind of a real important thing in chemistry. In the gas laws, we could use like M equals dRT over P or something like that to find molar mass, but that's only if the substance can be made a gas. Boiling point problems like this one and freezing points, the next one, work for a much broader classes of compounds, because compounds that can't get into the gas, maybe you can make them freeze, or maybe you can make them boil in a solution. So there's a lot of utility to these kind of problems. Anyway, solving them is pretty chill. We have a delta T. It's the difference between the solution boiling point and the pure solvent boiling point. And we also have a K. So the first thing you want to do is you want to solve for the molality. So here's delta T, the difference between the solution, 62.22, and the pure solvent, 61.70, delta T, 0.52 degrees Celsius. Now we've got delta T, we've got the K, that 3.63 number. We can solve for the molality. Molality equals delta T over K. That comes out to be 0.14 molal. And that number again, 0.14 moles of BHA over kilograms of solvent chloroform. Well, we can turn 25 grams of chloroform into kilograms and knock that out of the molality. So 0.14 molal is 0.14 moles BHA per kilogram chloroform. We're going to multiply it by the kilograms of chloroform, 25.0 divided by 1,000. We get 0.0035 moles BHA. Now remember, molar mass, which is what we're after, it's grams divided by moles. So if you take that 0.640 and you divide it by 0.0035, 180 grams per mole. That's the molar mass of BHA. And for a chemist, this is a cool number to know. There's a lot of uses for molar mass. This is one way. You can use it in a boiling point elevation problem like this one. We might be using aluminon at the end of Chem 223. It makes aluminum turn kind of a pink color. It's pretty cool. But anyway, the process here is going to be very, very similar. We're going to start by doing a delta T. Molality will be delta T divided by K. And remember, like on everything else, molality here must be a positive number. Notice how it says it freezes at a negative number. So remember, negative delta T's are fine, but you don't want to have molality be negative. So in this problem, technically, you can think of it, it's 0.197 degrees lower than usual, 0.197 lower than 0. So 0 minus negative 1.97 would give you 0.197. It's just as easy. Think about this whole thing as just absolute value. And again, absolute value means if anything's negative, make it positive. Molality must be a positive number. You can have a negative K and a negative delta T. Make sure that your molality once again is positive. So this molality, 0.106 moles of aluminon per kilogram of water. We can get rid of the kilograms of water. 50 grams of water divided by 1,000, 0.0500 kilograms. So the molality times the kilograms, 0.00530 moles of aluminon. And remember, molar mass is grams divided by moles. We put 2.50 grams of aluminum in. You can divide it by the moles we just calculated. Aluminum is a pretty big molecule, 472 grams per mole. So again, freezing point lowering and boiling point elevation are really awesome for finding molar mass. And you might have the most up-to-date, coolest piece of scientific equipment which spits out a molar mass, but are you sure it's calibrated? Are you sure it's working right? These are the things that scientists literally freak out about. This is a pretty easy test to make sure that your cool instrument, top of the line, hundreds of thousands of dollars, whatever, make sure that it works, all right? This is a nice way to verify that all of your equipment is up to speed. And trust me, this can be pretty important in science. The last of the colligative properties is what they call the osmotic pressure or osmosis, all right? Osmotic pressure is literally a pressure of solution. So in this problem, we're trying to find the osmotic pressure of human blood at 37 degrees Celsius. Now, we're going to assume that human blood is isotonic, which has the same ionic strength, as 0.154 molar sodium chloride. And we're also going to use a theoretical Van Hoff factor for sodium chloride. Okay, so a couple things here. First of all, when you're talking about osmosis or osmotic pressure, we first need to think about if you have an ionic compound. And this actually applies to both freezing point and boiling point questions as well. Now, ionic compounds like sodium chloride have a positive and a negative. So in this case, it's a positive sodium and a negative chloride. All of the colligative properties are about number of pieces running around in solution, and that can include ions. So sodium chloride theoretically breaks up always into a sodium plus and a Cl minus. You get 1 plus 1, 2 pieces for every 1 NaCl you put in. So when they talk about theoretical Van Hoff I factors, it's literally equal to the number of ions. So the I factor in this problem is going to be 2. Now, every other problem we've done so far in this problem set has involved organic molecules. Organic molecules do not dissociate into positives and negatives. So we haven't had to worry about Van Hoff factors so far, but we are going to worry about this one. If you have an I factor with freezing point, it would be delta T equals K times M times I. And boiling point would also be delta T equals K times M times I. But again, we haven't worried about I factors so far because, again, they've all been organic molecules. In this factor, though, we definitely want to do the I factor of 2. So osmotic pressure is pi equals I CRT. And again, if everything was organic, you wouldn't have to worry about I, but we are worrying about it here. Now, R here is the good old gas R, 0.082057. We also used earlier the so-called energy R, the 8.3145 number, but in this one we want to use the gas R. We have to use a Kelvin temperature. The osmotic pressure is going to be an atmosphere of pressure, believe it or not, which is totally crazy. And up here we have the concentration. It's molarity. It's not molality or any of those guys. It's good old molarity again. So we've got all the pieces we need. We turned the Celsius temperature into Kelvin. I did put a little dot right there because the one spot is significant. We don't want to have it not be counted. Oh my. Anyway, pi equals I CRT. So I is 2, concentration 0.154, R, the gas R value, 310 Kelvin, 3 sig figs. The I factor is just an absolute value. Don't worry about that for sig figs. 7.83 atmospheres. So this example of human blood has a pretty appreciable pressure. 7.83 atmospheres is nothing to sneeze at, shall we say. So 7.83 is the atmosphere, or the solution pressure exerted by this sample. And that's pretty high. It's pretty crazy what this stuff can do. Okay, so that's it for problem set number 5, and I appreciate you spending your time with me. If you have questions on the material, there's lots of resources to help you out. Both in the companion and online, you can find a Chapter 11 study guide and concept guide that will be helpful, and I encourage you to check those out. There's also the online-only chapter guides, which are available to have more information on materials to help you learn the material from chapter 11. There is the important solution calculations handout that I recommend. Make sure you know how to go from molality to weight percent and molarity, things like that. Pretty important material. Okay, thanks for spending your time with me. I do appreciate it. Good luck with your studying and have a wonderful day.